Hello and welcome to another video. In this one I would like to show you how Thunderbolt was solved. Thunderbolt was one of the challenges from ångstromCTF 2021, which has just recently ended. Although it was crypto challenge, not reversing, which I'm doing almost, it was quite interesting. There was a bit of reversing part, but the crypto part was quite interesting, or maybe the solution was quite interesting, so I thought I will present this challenge. So we get a file which can be analyzed, and that's all what we get. Of course, we get an address where we can query the file in the server. So if we open this file into Ghidra, it's not a very complex challenge. The file is not that complex. I think it was even compiled with some debugging information. We can see that when the application runs, we get a message, enter a string to encrypt. We get that message. Of course, the flag is opened and we read some data. And then we also open dev urandom file and read some random bytes from that file, and we read two chunks of random bytes. One is 16 bytes and the other one is as long as the flag. And then we call two functions. One is fgen and the other one is enc, ends from encryption, and at the end we print the flag that is after the encryption. And if we look into this fgen function, it is quite similar to RC4. We have some kind of SBox initialization, quite the same as in RC4. We do have something that looks like key scheduling algorithm in RC4, but there are some differences. The one is that instead of 256 iteration, there's like 300 hex. And of course, or maybe not of course, but in this case we have those two keys that are being passed to this function. So basically those two random chunks of data that we query from urandom are being passed here and are used as a keys to the key scheduling algorithm. And of course, we don't know those bytes, what they are. And yeah, as I mentioned, the change is that it's a bit more iteration in those loops is being used here. But if we look at the algorithm is quite similar to RC4. We have some exchange bytes in this SBox. But what can be noticed, the exchange is done in quite an interesting way. It's being done with the XORing. So basically there is this XOR swap algorithm which can exchange values without temporary variable. It's like fancy swap algorithm because like normally you would use a temporary variable to store value that is being exchanged, or one of the values that being exchanged, but you can do it without this temporary variable using this XOR swap algorithm. And this is what it's used in this task. And it works quite okay, except for one case. The case that those storage places are the same, this algorithm will fail and it will not exchange, but it will zero out the value. So basically, in some cases where we have the same indexes that we want to exchange, it will we have the same value of the index, it will not exchange, it will zero out the values in this SBox. So we'll get not truly random values in the SBox, but in some cases we'll get some zeros. And of course, as in RC4, this SBox is used later to just XOR input the SBox and this is our output, which will be printed later. And as I said, it looks quite similar to RC4 and the exchanges of values in this Xbox. I'm not sure if that matters if it's similar to RC4. The important part is that in some cases we'll not get truly random values in this Xbox, we'll get some zeros. And we can see that because what we did, we actually write down the same algorithm in Python. So basically just to observe if the analysis is correct, and some values in this S box will be actually zero in some cases. And this is of course what's happening, because if we do not actually implement the same technique of zeroing out the values in case of A and J being the same, we'll get incorrect output. But if we do that, the output is the same. And yeah, I'm just like printing those zero values. So we can see some indexes are, at some indexes we have this value 0 instead of some random value. So idea to solve this task was that if we run it multiple times, because of this bug, let's call it, in the algorithm, that instead of a random value we'll get a 0, we will get the true flag value in this place instead of a random character. And if we run it multiple times, those true characters will be more often than the truly random ones. So we could actually detect what is the actual character on that place in the flag, because it will just stand out, because it will be more frequent than all the other random bytes. So this is what we did. We actually implemented algorithm that basically runs the binary, encrypts something, gets the result. So basically we get a hex result after we encrypt, and we analyze what we get and just build some frequency table of those bytes. Yeah, and just adds more and more from each runs. And the idea was, if it's correct what we thought, we will get a correct flag, correct bytes of the flag with some high enough n. So basically we thought it won't be needed to run it 2 million times, but for example 200 or 500 times should be enough to get the flag. And since we have the binary locally, we can actually try this out to see if it works. So I have prepared the file. So basically the chal is the challenge file that we get from the organizers. We have a flag file which is read by the task. So we have this, this is a fake flag to see if we can solve this challenge. And we actually have this script, so pawn tools, using pawn tools to see if we can get the flag. And if we run it, so it will run 200 times, or actually 500 times, but I think originally it was enough to run 200 times to get the result. And we can see if it will be a flag or it will be just some fake values, which actually then it would mean that the theory was not correct and we cannot extract correct bytes due to this 0 bytes being present in the S box. So the algorithm is running and we should see some output in a moment. So basically right now the application is started, but I know what happened. So basically I run on the server, not the local. So basically I need to add a flag local, and then it runs actually locally. And before it was querying the server, organizer servers, and of course it will work, but it is much slower. But we can see that we get something. It's not completely the flag because some of the characters are not correct, but basically we are getting something. So we are getting some, this is a fake FPAG, but we could more or less make sense of it because it was just single characters that were not in place. And actually if we would run it on the server, we would get the same. I think it was like 1 or 2 characters were out of place, but yeah, more or less the flag was visible. And I have a run here. So basically this was the, well, actually here is some wrong character, but it was correct during the competition. But we can see that most of the characters are visible. And actually if we do not have all the characters, we could use this frequency table that it's printed here and run some more runs of this algorithm to get more data for the frequency table and extract correct characters. I guess it could be that here there are 2 characters that have the same values, so I guess the code was taking the first one that was in this table. But yeah, nonetheless the flag could be extracted this way. So it was quite interesting challenge. I'm not usually doing crypto challenge, but yeah, the way that it could be extracted because of this XOR quirk, let's call it like that, zeroing out the values in some cases, the flag could be extracted. It was quite fun. I had fun solving it, and I hope you like this description. And if so, please like and subscribe, and see you in the next video. Bye bye.